Okay, so while we're waiting for Diganta, I've sent a message to him, so I hope he'll show up. I'll just revise a few points on the loop invariant discussion that we had yesterday. Okay, and then I will open up. Okay, remember this one. So a few things that I wanted to, I need to share just 1 minute. Okay, so I mentioned, I mean, you all understand what a loop invariant is, correct? So that I'm assuming, okay? So if you have any doubts about loop invariant, please ask, okay? If not, and as I've said here, this is something that some condition, any condition, that should be true the first time you get to the head of the loop. And if you assume you start with an arbitrary state that satisfies the loop invariant and execute the body of the loop. Yeah, this body of the loop, then that is the second part. And it will be true. And you assume the starting from an arbitrary state that satisfies even of x. And if the loop entry condition holds good after you execute the loop, the predicate continues to hold after you execute the body. So checking this can be done as earlier, okay, on code which does not have the loop. So for example, the initiation condition can be checked by checking this one, that the code before the loop, if you start from pre condition and then execute the code, all the code from the beginning of the program till the head of the loop, then I is satisfied. So for this particular example, that involves actually checking this one, that if even of y is true, which is the precondition, and you execute the fragment of code before the loop is x being assigned y, then even if x holds good. So that which can be proved, checked by deriving a VC verification condition for this piece of code. As you can see that this is obviously true because y, if you assume even of y, then after you execute that, even of x will be true. The inductiveness check is, as I said, involves checking if you start from an arbitrary state. So it's the emphasis on arbitrary state is very important, okay? It is not the state that you get, so that is, you forget about the pre-code, okay, the code before the loop. So you just start with a precondition where you start with in a state in which the invariant holds good, which in this case is even of x. That's what invariant holds. And the state is such, the values of the variables are such that you enter the loop entry condition holds good. And then you execute the body and you have to check that the invariant continues to hold. So for this instantiator on this example, this consists of proving this about the body of the program, that if even of x is true, from any state in which even of x is true, and if x is less than 10, and if you execute the body, which in this case is x is equal to x plus 2, even of x holds. Okay. So that's what this thing says. And I mentioned that a loop invariant represents an over approximation of the loop. Okay. You know, in this particular case, the even if x indeed represents in the following sense, that it includes the set of all possible values that are actually assigned for the variables during all iterations of the loop. As you can see, even if x is certainly, you know, in this case, that happens to be the exact precise set of values as well for this program. Because if you start with the precondition even of y, then it is the case that in the beginning, even if x is true, you're in a state in which x is even. And after you, you know, every time you execute the loop, since you're incrementing it by x plus 2, even if x holds good. So the set of values that that you get is exactly even if x, because you know, this also includes even values. X can take even values which are greater than or equal to 10 as well. So in this case, even if x exact denotes precisely the conditions. Okay, that predicate even if x denotes precisely the set of values that it takes. Now, it can in general be an over approximation. Okay, for example, if say instead of the precondition even of y, let's suppose that suppose I had initialized x to 0. Okay, instead of y, here I'm initializing to y, and y I'm allowing y, I'm constraining y to be even. Let's suppose I start by initializing x to 0. Even then, this post condition holds good. And your loop invariant, suppose x is equal to 0, that's the case. So even if x is also a loop invariant, prove that. Correct, Ameya?
Yeah, so it is still, it will still accept everything. Yeah.
Yeah, but in that, you know, for that thing, even if x, you know, is an over approximation, correct? Because even if x, if I replace this loop with something like even if x, like you know what I'm saying that I could do, because you know, when if x is equal to 0, then the set of values at the head can only be something even and which is less than or equal to 12, correct? Because I think so, even of x, which allows for includes values that are greater than or equal to 10 are also included. So in that case, also you could do the replacement, but even if x for that program, in that case for the loop, it will be an over approximation. But that doesn't matter, as you just now observed that a loop invariant is also okay. So, and that's why it is okay to replace the loop with a code like this, okay, with the over approximation. Of course, there are several things in here that I've used which are not exactly something that a construct that you find in a program, okay, in a traditional program. That's why I want to take a moment to explain here, if you had. So this, what I have here is an assignment, just like I had x and y is equal to 0. It's a non-deterministic assignment, okay, which you don't find usually in regular traditional programming languages. What this states is that it says that I can assign x to any value, an arbitrary value, any value that satisfies this predicate. Okay, that's why it's I call it non-deterministic. It's typically called non-deterministic assignment that satisfies some predicate. okay, that condition. And then, and this assume is like saying that from here onwards, you may assume that x2 is greater than or equal to 10, which is actually the negation of the loop entry condition. Okay, and since I'm assigning any to x, assigning any value that may in this that may satisfy the loop invariant, but I want to make sure that when I exit here, since when I exit to the point where the post condition, of course, you will do that only when the negation of the loop entry condition is false. So this is almost like saying, to ensure, this ensures that whenever you come here, the loop exit condition holds true. Okay, so and that's what you should interpret this as. So when you so is that clear? It's like if you really want to replace that assume with a traditional programming construct, it is saying if x is if x2 is greater than or equal, if x is greater than or equal to 10, ignore the 2 here. Okay, so that's a mistake. So then you jump to this, the location at which you have post. Otherwise, you stay there. Okay, otherwise go to the same thing. So it is as though that you are looping there. You're staying there until it and you get here only if x is greater than or equal to 10. So so that's how you have to interpret this program as. Okay, so so you're allowed to assign, x can take on any value that is described, that satisfies this, that is in that set of values that the loop invariant is met. And so that's how. So is there, so when you construct the SSA formula using SSA notation for this thing, pretty much what you will have to do is assume will just involve taking a conjunction of all the SSAs that you generate from the code, including this one, and you have to take the you also have to take the conjunction of this condition, because this is what it is claiming is you can only reach here if this condition, under the assumption that this condition holds, which is the loop exit condition. So that's what it is. So so as I've stated here, so entry check is entry in inductive check, as I've explained before, consists of doing these two, checking these two codes. The exit check is done by replacing the loop by an assignment that is compliant with the loop invariant, and then you derive the verification condition corresponding to this program, which that you get by replacing the loop with a non-deterministic assignment, followed by an assumption that you reach the post condition, that is you exit the loop only if the negation of the loop entry condition holds true. So these are the three things that you will have to check in order to. The first two is the check to prove that what you have proposed, the predicate that you have proposed, is indeed a loop invariant. Okay? And the exit check is actually saying if you exit the loop, then the post condition holds true. Now, in this case, the post was attached. There was no code following the loop. But if there was code, then you will have whatever that code after the loop in between the assume and the post condition, and you would then generate the verification condition for that program. So that portion here is empty because there is no code, and that's how that you would do. Okay. So that's the, yeah, those are the points that I wanted to make. And yeah, especially this program, which assumes and non-deterministic, constrained non-deterministic assignments. Okay, so in which you will use assignments based on certain conditions. Okay, any questions there? So before I pass on the control to Diganta to start his part.
No, sir, no questions from me.
Okay. So I have uploaded the first assignment, which consists of some games that yeah. So for you trying to solve the two games that I had introduced. So those are the first two questions, and here is the thing. And there are some questions about regarding what for you to do a few problems based on the material that I have covered in the formal verification basics. So where I'm asking you to check certain pre and post on some simple programs, some of which includes I haven't given you the program here. So I'll upload. Okay, so there is a program missing for problem 3, which I haven't shown you, which I will give you. Okay, sorry. So there is a program missing here. Okay, so I will add that. So, but you could start cracking on this. Okay, so this I've already uploaded. Please review it, and if you have any questions, send us all email. Okay, send email so that clarified. Okay, I'll stop share.
So, can everybody hear me?
I can hear you.
Yeah.
Okay. So should I start sharing screen?
Yes, please.
Okay. So yeah, so basically I'm going to go over some of the basics of training DNN, what it involves from a theoretical point of view, not in too much detail, and then I'm going to move on to showing how you can train a DNN using PyTorch. So, okay, so I think almost everyone probably remembers this, but just a quick recap of DNN, what DNNs are. So you have multiple layers in a DNN, and each one of those layers consists of a linear layer, which is actually something like an affine transform. So this, for example, is the first linear layer, and that will take your inputs, multiply with them with some weights, add some bias to them, and the resulting value is then passed through an activation layer. So the activation layer, in our case, we always are going to use the ReLU function, although there are many multiple different activation functions that are used in practice. We'll mostly stick to ReLUs because those are the easiest to handle from a verification point of view. But
anyway, now here I want to briefly interject. So the material that is being covered here and by not the training part, at least the modeling of DNN and some of the basics of verification, and as well as these activation functions, how to model them, etc. They are in that book on verified deep learning. Okay, so I think chapter 1 through 3, you will find them there. So, in case you want to refer to them, yeah, so that you could go look at them. And there they have discussed a few other kinds of activation functions and actually how to model them as well.
Yeah. Yeah, so they in that book they have gone over um, those kind of things. So okay, so basically, this is the idea of what the DNN is. Now, before we come to training a DNN, we have to understand what the parameters are. So these weights and the bias values that you are multiplying each one of the inputs and adding to the inputs, these are the parameters of the DNN. So essentially, the training process is going to adjust these values so that the DNN behaves in certain ways. So what we're trying to do when we're trying to train a DNN is to find good values for this parameter so that the DNN approximates the function that we want the DNN to approximate, right? So let's look at the overview of the training process, what it is at a high level. Okay, so essentially, there are several problems in the real world where we don't the exact behavior that we want to define or that we want is very hard to define precisely and exactly, right? So for example, if you want to write a program to say recognize the images of cats, right? So I'll input an image and I'll ask you to say whether it is a cat or not. Then this is somewhat hard to do, right? Because how do you even go about writing a program that looks at the pixel values of your image and decides whether it's a cat or not? So these sort of problems, we have something of an intuitive understanding of what we want, but oftentimes we have a hard time defining it in terms of a precise algorithm. So you can't use conventional programming to write a program that classifies an image as a cat or not a cat, right? There are similar issues with other sort of domains where you might want to use some, like you might have some intuitive or some specific ideas. So for example, for pricing used cars, you can come up with a very precise model of pricing used cars, but maybe it does not fit your data, right? You have a lot of data for pricing used cars, and it turns out that your model is a very loose fit on the data. So instead, if you can come up with, or if you look at a very savvy salesperson, then that person can actually come up with a very good price by just looking at a car, and he won't be able to tell you exactly how he does it. It's some sort of intuition, right? So how do we try and capture that in terms of a program? So that is the sort of the intuitive motivation behind machine learning. There are these problems where it's hard to define what we exactly want to do. However, we do have data. That is, we do have a large number of examples of what we want. So for example, when we talk about classification of images of cats, we have millions of images of cats online. Like you can easily download several thousand images of cats, and you can download databases containing millions of images of cats if you search at the right places. Similarly, you have large records of car sales, right? So what kind of car sales at what value at what location and so on. So in machine learning, what we want to do is we want to take all of this data, this large amount of data, and we want to fit some parameterized models to the large sets of data. So for example, if you remember what a DNN is, it is essentially a parameterized model, right? It's a model, and there are some adjustable parameters in there. So we want to take any parameterized model and fit it to the large set of data. So before we, so let's talk about some nomenclature in terms of in the machine learning thing world, let's say. So we talked about two examples, right? Pricing used cars and recognizing images of cats. So whenever your model is supposed to output a value that is like a smooth value, an output value, that is usually called as a regression problem. Instead, if your model is trying to classify a particular input into multiple categories, they are called classification problems. So these different sort of problems are dealt with using different sets of heuristics. So it's somewhat important or a good idea to know the difference between them. But usually this is not like, it's not a very fundamental or deep difference that is there. It's just a difference in nomenclature depending upon what kind of values that your model is supposed to produce. Is it supposed to classify something, is it supposed to give you a Boolean or a discrete answer, or is it supposed to give you a smooth answer? So yeah, so for example, if you want to talk about the regression case, what does a model do? It takes an output and it takes an input and predicts an output or classifies, right? So depending upon whether it's a regression or whether it is the classification case. So this is for regression and this is for classification. And so images of a cat is an example of classification, and then say output the price of a card is an example of a regression, right? So an example of regression would be this one.
I have a small doubt.
Yeah.
Here you said output probability of it being a cat. So when you do that, you still consider it a classification problem, or is it, because now it's no longer, you're not outputting a discrete value right now?
Yeah. So it is still so as I said, this distinction between classification and regression is not something very deep. It is still considered as a classification problem, and most classification problem models will actually be designed to output probability values, and we'll sort of come to why we want, like there are some reasons as to why we want to do that. So usually whenever a model outputs a probability of something happening, in practice that is sort of seen only in classification models. So
Okay.
yeah, but in general, what I want to talk about, I think this is a somewhat more interesting point to ponder about, which is that you can actually, whether it's a regression problem or a classification problem, you can think of a model as a parameterized probability distribution. So for example, if you have, say, in that sense, the output could be a probability of it being a cat, right? So say, for example, instead of taking just an image and saying cat or cat or not cat, you could give a sort of estimate as to what you think the probability of that image is of being a cat, right? Similar sort of transformation can be done to convert your regression model into a model that is producing a probability distribution, right? So if you have, say, if you took some data of the car, so you have car, the car color and make and such data, and you are outputting a price. Instead of outputting a price, you could output a function that takes a price and gives you a probability distribution, right? Or gives you a probability of that price being a good price for the car. So in some sense, then your model becomes something, you can think of your model as something that takes in all the data of the car and takes in a price and gives you a probability, right? And so you can think of a model that is supposed to give you a car price as being a model that will give you a probability distribution of the car price. And you can implement this in practice by doing something like, say if you already have a model that given some data on cards, so it will take some data on a card and give you a price. Now what you can do is you can take this price and say you have set some standard deviation. So you set like you fit a normal distribution around this price as your mean with some preset standard deviation, right? And then that will give you a probability of any other value of the price. If it's very far from the price that your model outputs, then your probability is really low. If it's very close, then your probability is really high, right? So in this sense, you can also think of models that produce smooth outputs as being parameterized probability distributions. And this has some advantages in terms of the way we can deal with it mathematically by thinking of it as parameters probability distributions. So this is what models are. What is your data, right? So very simply, your data is going to be just some input output pairs. So you're going to have, say, for example, for cars, you're going to have the car make, the miles, the color, or whatever, and then the output is going to be car price, right? So this is the most basic sense in which you can think of data. It's like it's an example and the correct input and a correct output, right? So examples of what the behavior you want. But if you can think of parameter like a model as a parametric probability distribution, there is an analogous way of thinking of data in terms of probabilities and distributions. You can think of your data as being a sample coming from an unknown real world distribution, right? So for example, let's say that you have a large collection of images, right? And you can say label each one of those images as being a cat or not a cat. Say I've manually done that. So you have, say, downloaded 5,000 images of cats and 5,000 random other images and mix them all together while maintaining labels. So now you have a data set where your input is a cat and you have the corresponding correct output for each image, whether it is a cat or not, right? So your input is an image and your output is a cat. So that could be one way you look at that data set. Another way you can look at that data set is that your universe consists of like images. So you have a set of images, and some of those images are cats and some of them are not, right? So that basically gives you a probability distribution on this set of images of something being a cat. So you can think of some unknown abstract function or unknown abstract probability distribution that, given an image, will give you the probability of it being a cat, right? So does this make sense?
Yeah.
So I will just draw this here. So okay, so basically then this entire data set becomes something like an unknown real world distribution that you're actually trying to find out, right? So what you're trying to do in some sense then is you're trying to approximate or come as close as possible to this unknown real world distribution by tuning or modifying the parameters of your parameterized probability distribution. So then what you're learning becomes is trying to come really close to this unknown distribution using your parameters probability distribution. So in terms of whether you think of your data as just input outputs or a sample from the real world distribution, and whether you think of your model as taking an input and giving an output, or as this parameters probability distribution, you can think of your loss function in two different ways as well. So in general, a loss function is something that's going to take the model's output on the given input data and generate a single real value representing how well the model fits the data. So this is, in some sense, tells you how good your fit is, right? So your training is going to try to minimize this loss function so that your fit is going to be better and better. So again, we were looking at parameterized models as in terms of two perspectives, right? One perspective is just being just something that takes input and puts an output versus being probability distributions. In a similar way, you can sort of look at loss functions in two different ways, and you can come up with two broad classes of loss functions. There are many different loss functions, and they usually fall into one of these two broad classes, but there are also various loss functions that are very difficult to put into either class, and that are definitely not in either class, and so on. But for now, let's look at these two broad classes. So if you look at your model as being just something like a function that takes an input and output, right? Then your data is also going to be just a set of known inputs and outputs. Then you can think of your model as being just or your loss function as being just taking the distance of the output that your model produces to the correct output, right? So what you have is something like let's say you have X and Y. So this is your training data. So this X is an input and Y is the correct output according to your training data. So what you can do is you can take this sort of a thing, right? So let me just make this smaller. Yeah, so you can take this sort of a thing. You can take the sum over all your training data points, and say your model is M, then you can take the distance between the output of the model and output of the model and the correct output that you get, and take that sum. So this is going to give you a loss function. Of course, over here, I'm using Euclidean distance. You can use all sorts of other distances, but if you do use the Euclidean distance, what you get is known as the mean square error loss function, because it is the mean of the square of the error between the actual output that you want versus the output that your model gets, right? So if you think of your model as taking inputs and producing outputs, then you get this class of loss functions that are based on some sort of distance. And the most common one of them, or at least one very common one of them, is this mean square error loss functions. Now, this works very well for regression, not so much for classification. Why? Because you see, for regression, you already have, you know that the output of your model is going to be something smooth. It's going to be a real valued number, right? So even if you don't have too many data points, you can actually vary your, like, it's possible that as you vary the parameters of your model, so remember your model is parameterized, and as you vary the parameters of your model, the output, these MXs, can slowly get closer and closer to Y, right? So this means that your loss functions in some sense is going to behave somewhat smoothly in case of regression. And this smooth behavior actually really helps the training algorithms, and we'll see why that is the case when I talk slightly about the gradient descent. Whereas on the other hand, if you're trying to use something like this for classification, then let's say that your model is going to produce either 0 or 1, right? So your model produces 0 or 1, and your Y is also 0 or 1, right? So then each one of those terms in this sum is either going to be 0 or 1. So what happens is now your loss function is always going to be an integer. So for classification, if you use this, your loss function becomes an integer, or your loss value will always be integer. And that is not a good idea. Like, that is not a good situation to be in, because then in that situation, what happens is that you might end up, like, if you make a very small change in parameters, you might not see any change in the loss function at all. And then you make a really large change, and it turns out it's in the completely wrong direction, and you had no way of knowing because a small change wasn't giving you any response, right? So it becomes hard to tweak the parameters if your loss function is discrete and integer valued in this sense. And that is why usually this mean square error is not used when your model is, you're treating your model as just taking an input and producing an output, but your problem is a classification problem, right? Does this make sense? Yeah. So, and this is the reason why when we are actually going to train classification problems in real life, what we're going to use is this parameterized probability distribution perspective. So if your model is a parameterized probability distribution, then what happens is that you can think of a measure of how good your model or how close your model is to this unknown data distribution, this real world distribution, is that you can think of what is the probability of producing the data that you're seeing if your model was a real world distribution, right? So essentially what you have is you have some unknown real world distribution, say PU, and that has sampled some data, right? Now, if your PU was going to be the model, like if say the probability distribution given by your model is M, and if M is basically the same distribution as PU, then the probability of seeing the data that you're sampling. So let's say that the data that you have sampled is just x1, x2, and so on. So the probability of seeing the data that you're sampling is going to just be the product of product over I of M of xi, right? So the probability of seeing this data, this is going to be fairly high if this xi was actually a sample coming from P, right? So if xi was a sample coming from this unknown probability PU, then this is going to be large, right? On the other hand, let's say that this unknown probability PU and your M have no correlation whatsoever. Then the probability of you actually generating this specific sample, which is coming from a completely different unknown distribution rather than the distribution given by your model, is going to be low. So you can take this as your loss function. But of course, this in itself is a somewhat cumbersome process to deal with, and this this is called the likelihood. There's an entire class of loss functions that comes from likelihood, and this idea of comparing the unknown probability with the probability distribution coming from your model. But the most common one is called the negative log likelihood. Sorry, this is a typo. This should be log, not loss. So let's make the change here. Negative log likelihood. So the negative log likelihood basically takes its log. So you take the log of this, and so that will basically reduce to something like this, sum over log of mxi. And then finally you take a negative value, because if you take the log, then the bigger your probability distribution is, the more positive the value of the log of it would be, right? But you want your loss to be some function that you minimize. So that's why you take a negative. And then what you end up getting is a positive function, because remember, since this is always less than 1, the log value will be less than 0. So if you take negative, it will be greater than 0. So what you end up getting is a positive function that when you minimize, you can say with some confidence that your model is close to the unknown probability distribution that you sampled your exercise with. So this is the negative log likelihood probability distribution, or negative log likelihood loss, sorry. And usually when you use or when you train classification models, you use some loss that is coming from this idea of comparing probability distributions, because in classification based situations, you can sort of, this actually naturally comes around, right? There is no problem, like it is not wrong to use this in regression based situations. So basically, you cannot essentially reliably use, say, a distance based loss in a classification situation, because your loss is going to end up becoming discrete. This loss will actually still work in a regression situation. This still works in a regression situation, but it's not necessary. Like, you don't need to use such a complicated loss function, or at least computationally somewhat complicated loss function, if you're dealing with a regression problem, because then you can just use distance functions, which is much easier to work with and compute. And an interesting thing is that this mean square error, so this, if you take, say, a regression model, and if you do this sort of procedure where you take the output of the regression model and then you fit a normal distribution to it, then what happens is that if you then try to calculate what you'll get if you apply the negative loss likelihood loss on this particular model, this probability distribution that you've gotten by fitting a normal distribution to your regression model, then it will actually reduce to the mean square error loss. So in some sense, mean square error loss can actually be derived from the negative log likelihood loss. So it's almost like the negative log likelihood situation is more general, and one can argue for that, but both of them have their particular places. So is this okay? Or I feel like I may be going a little, like brushing over a lot of things and going a little too fast, because I don't want to delve too deep into these things. But does anyone have any questions? Yes, no?
No, I think I am clear.
Yeah, okay. So this is basically the idea of what the loss function is. So remember that the loss function in some sense gives you a function, although the way I have defined it, it is something like it takes the model's output and data and generates the real value. You can think of it as a function on your parameters. And that is the key point based on which the training process will operate, right? Because if you look at it, your xi's, so let me actually write over here. Your xi's are fixed, right? So this xi, the sample that you have of a number of xi's or xiys are basically fixed, right? Your theta is something that theta is the set of parameters, let's say. So parameterized by theta, let's say. So your theta is what's going to vary, right? So you can think of your model as the output of the model as being a function of two things, right? The x, the input, and theta. So then your loss becomes, you can say if you take the negative log likelihood loss, your loss becomes a function that looks something like this, right? So if you fix your xi, which is usually the case when we're training things, because our training data is going to be fixed. So if you fix your xi, this actually becomes a function of theta, right? So you can write this as L theta. So we can define the loss function as being a function on theta. And this will basically directly give us a function that we want to optimize. So we want to optimize this function taken as a function on theta. So one can think of the training process as being an optimization process where we want to optimize this loss function on theta. So far, is everything okay?
Yeah.
Yeah. Okay. So now let's. So I think this is like I at least think that this is a fairly interesting.
One clarification of question. So theta there is the actual output produced, no?
No, the theta is the output of the learning process, but for a DNN, for example, theta is going to be your weights.
Weights, yeah. Okay. So that, yes. Okay, which determine what it actually produces.
Yeah. So theta is going to be, let's say, your weights, biases, and so on. So theta, we can think of this huge set of inputs. So you can think of your DNN as something that takes a certain set of weights and a certain set of inputs and produces an output. So as a function, one can think of it that way. Okay. So yeah, I really think that this is like a very interesting question. And I mean, at least usually when I have seen most places where people like talk about machine learning, they don't really go too deep into this question, although there are some people who are really working on this question at a theoretical level from what I've seen. But why DNNs, right? And in fact, if you do a comprehensive course on machine learning, you'll find that DNNs are not the only machine learning model out there, but they're by far the most popular and the most successful, right? So there are many other models there, like, you have your decision trees and various different models. So why are DNNs the most popular and why are they like the most successful things? So I mean, of course, I don't really have a very good answer for this, but I have some points along which we can think about this, right? And I think those are also interesting from a verification perspective as to, understanding what it is exactly that we're trying to verify, what kind of a thing it is that we're trying to verify. So I think, one can sort of think of a DNN as being built from a number of simple linear models, right? So linear model, let's say a linear separator, or a linear regression function is the simplest model you can think of. So say you have a bunch of, let's say that you want to separate red points from blue points, right, on a 2D plane. So you have a bunch of red points like this, and say you have a bunch of blue points like this. Then if I tell you that, okay, all your model is allowed to be is this linear separator that is going to like your parameter is going to fix a line. So that's going to fix, like, say, a slope and intercept. And your model is going to say red below this line and blue above this line, right? So maybe your linear separator is something like this. So then you can actually do the entire machine learning training process for this and come up with a line. But of course, as you can imagine, this is too simple and it cannot express more complex distributions where the points may be more thoroughly mixed, right? So let's imagine some set of points like this. Or okay, I'm gonna so I'm gonna maybe not draw the axis like this yet, because so maybe let's imagine a set of points that are spiraling around each other in some sense. So let's say that we have red points like this.
So Diganta, can you hear me?
Yeah.
Yeah, Diganta, sorry, my mic was not working. I had a question in the last slide. I could not.
Yeah.
See, so here I'm just trying to gain an intuition as to why this loss function is a good loss function, the one that you wrote below.
This the negative log likelihood one, right?
Yeah. So if you could just give me some intuition as to why this is a. See, there it makes some intuitive sense, right? Because y is the expected output and mx is what the model is giving.
Yeah. So it's just a straight up distance, right?
Yeah. So in this one, why is this? I'm just trying to gain some intuition.
Yeah, sure. So basically, so let's think of a model that is just a normal distribution, right? So your parameter is just going to be some mean and some standard deviation. So wait a second. Yeah. So let's say that your model is just some mean and some standard deviation. Then if your model is say if this is your unknown distribution, right? So unknown distribution is also some like normal function, and it's something like this, right? So then when you sample your data is going to be around this peak, right? So you'll have more samples over here and very few samples outside. So now if your model is very far from this, say your model is the model that you're training currently is still a normal distribution, but it's peaking somewhere over here, right? So then, if your normal distribution is very far from this normal distribution, then the probability of you peaking these many points so far away from your mean is going to be very low, right?
Correct.
So in some sense, as your model comes closer and closer to this unknown distribution, the model's distribution, the probability of you picking the points exactly in the way that you've picked in this distribution is going to get higher and higher. And this will work not just for normal distributions, but for any distribution, right? So if you think of any distribution as being this arbitrary function that this dictates how the density of your xi points in some sense, right? So if this is, say, your unknown distribution, then your xi points are going to be distributed something according to this in terms of density, right? You'll have more points here, maybe less number of points here, maybe even more points here, right?
Yeah.
So then as your model, like if your model does not follow this, if in any place where the model differs from this, so say over here your model is predicting a higher probability than your unknown distribution predicts, right?
Correct.
So then the model is going to assign a high probability to seeing more points over here, but you're not going to see that many points here. So you're not going to get as much probability as you would have gotten if your model had peaked here instead of peaking here. Similarly, you have a lot of points over here, but these are falling inside a region which has lower probability, right? So these end up contributing low amounts of value to this probability because your model is peaking here and not peaking here. So does this in some sense make
it helps. Yeah. So this is a product over all points, or?
Yeah, it's a product over all the data points that you have.
Okay.
So it's the total probability of seeing this exact data set, right? So the probability of seeing any one point is mxi, and then you AND over all of that. So the probability of that will become the product.
Correct.
And then this taking of log is mostly for numerical stability. And
yeah. That part I got. Okay, sure. Thanks.
Yeah. So coming back to why DNNs, some justification for using DNNs and not any other model. So let's think of some spiral situation where with clearly a linear separator won't work, right? So here clearly a linear separator is not going to work for you. But still, if you can somehow find something that is piecewise linear, it will work. Right? So, okay, I wanted to draw this piecewise linear, but ended up drawing it as smooth. So let's, yeah. So if you have a piecewise linear function, then you can use that to separate out your blue points from your red points, right? So you can have a piecewise linear separator in some sense, and this function basically paints this entire region of space as blue and the other region as red. Okay, by the way, does anyone have any questions at this point?
No question.
Okay. Okay. So yeah, so if you have you can imagine that a piecewise linear function will work well, and it's not very far-fetched to think that a piecewise linear function will actually work well in a lot of cases, right? So I like to think of, like, I mean, at least this is some perspective that I kind of have, is that DNNs are a really good way of producing piecewise linear functions in a parameterized way. Like if you want to produce one line, then you can just do with two parameters. But if you want to do a piecewise linear function, then how do you organize that as a parametric model or a parametric function, right? In a very say compact way. If you want a really large number of pieces, let's say, so then if you just have, say, one slope and intercept for each line, and you define where they meet and which direction is it that things are classified as blue and so on, then that is going to have somewhat high, there is going to need a large number of parameters to represent a function. On the other hand, DNNs can produce piecewise linear functions using relatively fewer number of parameters, right? So for example, if you have, say, two inputs. Now let's say that there are two ReLU neurons over here. So each one of these ReLU neurons, if I draw this, say, a plane where the two inputs are varying, each one of these ReLU neurons is going to act as a linear separator, right? So there is some value, some line below which the ReLU neurons output is 0. So it's 0 over here. So let's label these two ReLU neurons by some color. So let's say that this is going to be green and this is going to be blue. So there is some green line below which things are 0 and above which things are going to slowly increase, right? That is the behavior of the ReLU. Similarly, there will be some blue line below which things will be 0 and above which it's going to be slowly increase. So now you can see that you've already ended up splitting your plane just by using one layer. You've ended up splitting your plane into sort of 4 piecewise linear regions. These two values, right? These two values again can form an input into another layer, right? So now what you have is, instead of having a plane, you have 4 piecewise linear planes. And if you have, say, 2 neurons over here again, say you have, let's say that this is red and pink, right? Red and pink. I don't want to gray. Okay. So for these red and pink things, for each part of this plane, you're going to get one red line and a pink line, right? So for example, let's say that you can have a pink line along here. Maybe the pink line goes along here over here. Maybe the pink line is something like this here and the pink line is something like this here, right? So for each one of these 4 pieces that your first layer produced, your second layer is going to like have one pink line and then one red line, right? So you're going to have another red line. Okay, actually I think it's an orange line, but yeah, another orange line here, another orange line, and so on. So now with 4 layers, what you've done is, the first layer split your plane into 4 pieces, and then the second layer split each one of those pieces again into 4 pieces, right? So just with 4 neurons, you've achieved so many pieces. of course, there is a lot of sharing of parameters in some sense between these pieces, but it does allow us to, have a really large number of pieces in a piecewise function with a relatively smaller number of parameters. So I feel like that could be one way of looking at why DNNs are, or one interesting property of DNNs in terms of why they are very good as approximators for functions and as models in training, right? There is another very interesting, or two other very interesting theoretical justifications for the power of DNN. The first is called this. Okay, are there any questions at this point?
No.
Okay, so the first one is.
So I have a question. Like, you say like verifying DNNs is NP hard. So like, is there any machine learning model in which like verification is not NP hard?
Yeah, I mean, for example, the linear separator model, it's not NP hard, right? Let's say even for models like your decision trees, it's not NP hard. Because because those models are in some sense more enumerative than DNNs are, right? So like, if you have a decision tree model, for example, then decision tree model is basically like each you have a decision tree sort of structure, and each decision in this node is some parametric function that is going to be learned. So like it's going to be some simple linear decision or something like that. So here again, like this is, you can still sort of, for each path that you take, what you end up getting is a linear thing. So you can still sort of enumerate all of your paths, and the verification problem for each path is of course fairly simple because it's linear, right? And you can enumerate all your paths, and I think you'll get polynomial number of things at the end. So remember here, the size is going to be ultimately the size of this graph, and not like there's not going to be an exponential blow up in your sense of size, right? So if you say something like this, then you have 4 paths here, but your graph is also of order of 4 size, and for each one of those paths is going to be like some particular piecewise linear function that has, say, as many pieces or polynomial number of pieces in the number of layers, right? So if you have 2 layers, you're going to have 4 pieces. If you have 3 layers, I think you're going to have 7 pieces, if I'm not wrong, right? Yeah, 7 pieces at most. So
yeah, but that is still exponentially with the number of depth, no? The number of
I think it increases quadratically, the number of pieces that if you add one line, one line to your number of lines producing a piecewise function, I think that adds quadratic number of pieces to your thing. So I think ultimately, in terms of size of this graph, it's going to be some polynomial thing, like polynomial enumeration that you'll have to do. So since there are only polynomial number of pieces, you can just enumerate over all of them, and you'll not go into some exponential situation. So if I'm not wrong, I think the number of pieces that have, if you add one line, is something like n into n minus 1 by 2 plus 1.
The incremental addition is polynomial. That is what.
Yeah. Which is why if you add one more layer, that is going to add exponential number of nodes, but that is only increasing your input size exponentially, right? So ultimately, in terms of complexity, nothing increases exponentially. Your model itself becomes exponentially larger if you add one more layer. So is this okay?
Yeah. So you're saying that DNN is hard is because the activation function kind of is applied at every node, no?
Yeah, and then it's applied on top of other activation functions. It's like the composition of the activation function is basically.
Yeah, it's nested.
Yeah. Yeah, this nesting is, I think,
Is that, yeah, so that I hope it's clear for them. Yeah, so
yeah, if I think, like, if you have any questions here, if it's at least intuitively clear, or if you have any, if your intuition is telling you anything that you feel like there is something wrong with my logic, just say something like.
So if the activation functions were not ReLU,
Hmm.
would it mean
No.
that?
Hmm?
Hello.
Hello, yeah.
Yeah. So if the activation functions were not ReLU, would it mean that these are not just 4 lines like this? Or
Yeah. So let's say that the activation function was something like a smooth step function, right?
Hmm.
So then what happens is your lines is not just a solid line anymore. So it's not a piecewise linear thing anymore, but it's still something like, so if you take one neuron, the action of a single neuron is still something going to be like a smooth step around this line, right?
okay.
So I think what will happen in that case is you're going to have a smooth step along the green line, smooth step along this blue line, and so on. And then that will still produce these 4 different pieces, but the boundaries are not going to be these edges, but it are going to be more smooth in some sense.
Okay, sure.
And then there'll still be 4 other pieces for each one of these in the next layer, but things will be like, the steps would be smoother. I think that's how it's going to happen if it's, say, a smooth step function. So yeah, just I think I should probably mention this. I've been sticking to ReLU, but basically there are a number of activation functions, and one of the like common classes of ones are these sort of smooth step functions, which look graphically something like this. So if
Step
it goes from,
functions are above 0, right? Or
yeah, okay, so I was considered like pulling tan h into this class of step functions.
okay,
Yeah. So there's basically tan h and as you said, that normal step function. Yeah. And there are some other activation functions as well, which are not that commonly used. I think it's usually just tan h, sigmoid, or delu. Or at least that's the 3 that I recall seeing somewhere being used. Tan h and sigmoid are fairly common in like in terms of real world uses in machine learning, especially because they produce things like sigmoid produces something between 1 and 0, right? So you can call that as an output, like output that is coming from a sigmoid node can be directly considered as a probability value, which is good for classification problems. So okay, so are there any questions, or
So like for activation functions, like are there any like huge advantages choosing one activation function over the other, or it's like only small advantages?
so mostly it's about like the advantages, and as far as I understand, are in terms of numerical accuracy and things like that, because see, ReLU goes to plus infinity and stops at 0, right? So if you have a situation where you have huge inputs, then what you can end up happening is you can like end up getting out huge outputs or huge floating point numbers inside your DNN, and that can, and if at the same time you have very small floating point numbers, then that can cause problems. So with step functions and tan h, like with sigmoid and tan h, this sort of issue is reduced somewhat, but then the problem is that your input is or your output is bounded between 2 regions. So I think in terms of choosing activation functions, those are the concerns that people usually think of. Like, is it okay if this is bounded between 0 and 1, or -1 and -1, and is it okay if like I have huge values in this particular thing? But I think usually trial and error seems to be the best way. And usually people don't seem to mix and match too many activities. At least they don't seem to mix and match ReLU with the other ones a lot.
I think one of the reasons to also use ReLU is to minimize that vanishing gradients problem and all that, right? Over sigmoid at least.
Yeah. But yeah, I think that is fair. So basically, from what I understand, that situation is where if you have, say, a neural network that is very deep. I mean, this usually happens is vanishing gradient problems happens in things like RNNs. But but let's for now think of a network that is just very deep. Then okay, so I think I'll come to that when I talk about the gradient calculation thing. But basically, what happens is that as you backpropagate your gradient calculation, your gradients at the first layer might become very small if everything, if all the values of your neurons are near a place where you have, like, where you're in this part of your sigmoid or 10H activation function, where the gradients are really small. So okay, I'll talk about this in a little more detail, I think, if during when I talk about the gradient descent thing.
Yeah.
Yeah.
Diganta?
Yeah, I think
45 now.
Yeah.
So is this a good time, logical point to?
Yeah, I think this is a good time to start. I'll just state what the universal approximation theorem is.
Yeah, please.
Yeah.
Yes.
So the universal approximation theorem just says that you can approximate any function to any degree of accuracy. So if you have, and like intuitively you can, you can see that you can do that because you can make piecewise linear functions, intuitively speaking, with ReLU DNNs, right? So if you have, say, some arbitrary functions like this, you can actually find a DNN that will approximate this function to any degree of closeness that you like. Like you can fix an epsilon and then you can find a complicated enough DNN that approximate these functions to epsilon closeness. So that is what the universal approximation theorem states. And I think since I guess you guys have already read this particular point, and so I'm not going to state this again, but you can try to figure out how you encode a Boolean function in ON size with a neural network. You can also try and think of how you do the universal approximation as well. These are, I think, nice exercises to think about. Not, very difficult, but also it's fun to think about in an intuitive setting. So any questions? And if not, I'll stop.
That will be interesting. So can that Boolean function be precisely encoded like that? Or
Yeah. It is like it can be encoded very precisely. The only thing is that you'll have to always make sure that your inputs are like some zeros or ones. So if you stick to your inputs being just 0 or 1,
then I can understand. Yeah.
So, but yeah, otherwise it can't, right?
Yeah.
Otherwise, they'll always, the continuity of your neural network is always going to. Yeah. So, okay. So when I say approximate any function, I do mean continuous functions. So I should probably write this here.
Any continuous functions.
Yeah. I think, I missed this. Yeah. So I think this is a good place to stop. So if there are any questions, otherwise I think we'll continue next time. So next time I'll talk about gradient descent and calculating gradients, and then actually go into showing it on TensorFlow. And
then you'll be talking about TensorFlow also. No?
Yeah. So I say TensorFlow, although I think I'll be using PyTorch because.
Okay.
Yeah.
Any questions?